Still a little bit early, but I should get going. So today we want to look at work is equal to force times distance. We're going to do the single variable calculus version of force times distance. So we have a couple different kinds of units that will help us understand how we're going to put this together. Less from a physics standpoint and more from a math standpoint. So I'm not worried about so much about the physics of what's going on. I care about the math of what's going on. We know that integration is multiplication, but one of the factors is continuously variable. So we look around all our other disciplines and say, where can we find some multiplication? And then the eye of math Sauron looks over at physics and it sees work is equal to force times distance. And it's like, oh, that's some lovely multiplication you got there. It'd be a shame if one of those factors became continuously variable. So we grabbed it. The units of force and distance. Force is going to be measured in newtons. And distance can be measured when distance is measured in meters. And our units of Newton meters are renamed joules. Does anybody know if it's a capital J or a lowercase j for joules? Is it a capital J? I didn't look carefully when I was looking at physics for multiplication at their units, but you know, I knew it was joules, so I'll go with capital J. Go ahead and at me in the comments if you want. I won't even blame my students because they're the ones that told me it was a capital J. One thing to note is that newtons are units of force. So these are units of mass times acceleration. So newtons themselves are kilograms times meters per second squared. Because we got to remember that force is mass times acceleration. The other units that we can use for this, if we want to use imperial units, we measure force in pounds. If we're measuring force in pounds, then we'll measure distance in feet. So work units are going to be pound feet or foot pounds. This is also torque. I guess we're just going to have to know which one we're talking about. Note that pounds, we often take pounds and kilograms and put those two together, but pounds already includes gravity. The only reason that we can convert pounds to kilograms is because we're all kind of standing in the same place and gravity is pretty much constant where we are. So kilograms is mass, pounds is weight, and weight is force. Any questions? So just make sure we remember if it's problems in kilograms and you're off by a factor of almost 10, that's why. You just have to multiply by gravity. All right. Some other things that are going on here. For these problems, since we're playing single variable calculus, we only care about force that's going in the same direction as distance. our force is going to be moving in the same direction as the distance. So if we're lifting things up and it has a force, we're going to be moving it some distance. So here's an example of us trying to lift something up. Now it looks like force and distance are going in opposite directions. We just multiply by -1, that counts as the same. Left and right is one direction. Up and down is one direction. When we get into vector calculus, we have to improve our force times distance. We have to be more specific about our multiplication. In vector calculus, multiplication is going to be a dot product. So in vector calculus, we'll be calculating the dot product. Rather than just multiplying them. This is because of what the dot product tells us. So just a quick preview of a class that we're not taking until next semester. The dot product, but some of you might be taking linear algebra over the summer, so I want to mention it now. The dot product is how we multiply a couple of vectors, and it tells us how much of one vector is going in the direction of the other vector. So if we have a force as a vector and some distance down here, the dot product will tell us the components of the force in the direction of our distance, in the direction that we're trying to go. Oops, U is a unit vector. The reason I like to bring this up is, for the most part, this is familiar to you. You've done this before. It was just, but instead of just being some rando distance vector, some rando unit vector, you picked a horizontal vector, specifically a horizontal vector, and you broke the force into F cosine of theta and F sine of theta. And the dot product of F dot U is the magnitude of F times the magnitude of U times the cosine of the angle between the two vectors. So that's what the dot product is for. It's multiplication, but it's telling us specifically how much of one vector is going in the direction of, in a specified direction. What is this direction component of your force? But since we don't get to have vectors yet, because we've chosen hard mode for calculus, we only get one variable. We got to have the force under. We've already made this calculation. I've already resolved our force into a force moving in the same direction. This is not a new thing. Y'all have seen this before. We've got the angle theta, and you've got horizontal and vertical components. So let's suppose that we wanted to lift up 200 pounds, a distance of 12 feet. Notice that in this case, our force, 200 pounds, is going to remain constant the entire 12 feet. Work is force times distance. We get to multiply because our force was constant the entire distance. We get to multiply since the force is constant over the distance. If we had a problem that was written in SI units, I might say the same thing, find the work done in lifting 80 kilograms a distance of 4 meters. The thing we have to remember is that pounds is a unit of force, kilograms is a unit of mass. So I can't just multiply the 80 times the 4. I need to turn the 80 kilogram mass into a force. I didn't specify the problem was done on Earth, but we're going to have to assume this problem is being done on Earth. So we're going to need to throw in gravity to turn our mass with acceleration and then multiply by the distance. Any questions? Here, the number we get, we will write in joules. Kilogram meters per second squared gives us newtons. Newtons per meters give us joules. Once again, we get to multiply since force is constant over the distance. We have to include gravity we'll need acceleration due to gravity to turn mass into force. But we still get to multiply because it's constant. So lucky us. This ball is 3,200. 9.8 is almost 10. I just need to cut off 0.2 of this, right? And see, it's still too complicated, so. Any questions? Work is equal to force times distance. What are we going to do next? This is just multiplication. Work is equal to force times distance. Force was constant the whole distance, so we got to multiply. But this is calculus class. What are we going to do next? Same thing that we always do. Try to take over the world. Wait, no, that's Animaniacs. So let's suppose that we're lifting up a leaking bucket. Spelled D wrong. So this is the lifting a leaky bucket problem. The bucket was 200 pounds on the ground, but lost force continuously as it was lifted. So we can imagine it's a bucket with a hole in it. And that's the leaking bucket. So it weighed 200 pounds down here and it lost weight continuously. It lost force continuously as we lifted it up. So here we don't get to multiply because we did not have one force. Secretly, we're relying on, I'm relying on default thinking, which I shouldn't do. So I have to be more specific about something because I said the bucket was losing force continuously, but I did not specify how. So I should specify that. I really wanted to use the word continuously because that's the whole game with integration. So let's go with linearly. I was just momentarily obsessed with using the word continuously. In case you're wondering, we're going to trade out linearly for something else afterwards. We'll still go from 200 to 180 over 12 feet. We'll just use a different function to get there. So our assumption is going to be the same. We want to do work is equal to force times distance, but the force is continuously variable. So we're going to do the same thing that we always do when we come across this problem. We're going to assume that the force is constant for some small change in distance so that we can multiply. I just need to write the force as a function of the distance. The same thing applies as when we were finding volumes. When we're doing volume is equal to area multiplied by height. We need to define a variable to represent the distance in this case. I'm going to say X is the distance from the ground up to wherever the weight is. This means that I'm using the ground as X equals 0 feet. And the roof as X equals 12 feet. This makes it easy to write our force function. Force starts off at 200 and decreases by 20 pounds over 12 feet. We're going to use this force for some small change in height. So I'm going to say, if I just move a short distance, say delta X, the force won't change that much. Right, this looks like too much like IDX, so I don't want to look like I'm advertising for Volkswagen or something like that. However, if Volkswagen wanted to send me one of their new electric vans, then we'll talk. I don't think that's going to happen. But if I show up in a new electric Volkswagen van, guess what's going to happen in class? So if delta X is small enough, the force isn't going to change that much. So our work will be the force. I guess I can get, no, it doesn't matter. Times the distance. Now this is the work done just to move that little delta x. I have to add up at this point. The weight is smaller, so I recalculate the force and move it another delta x. Then we just add up all these works. So our total work will be the integral of 200, spelled 2 wrong. Got to make sure our delta x becomes a continuous dx. And we just integrate over all the values of x. So from 0 to 12. So instead of multiplying the force times distance, we end up integrating the force over the distance. And because it's Monday, right after the time change, there's no way I would be able to do this other than Math 9. You can see I'm not even trying to simplify 20 over 12 because I don't think I'd be able to do it. See, told you. Is that what you want? Oh. Too many parentheses. Note that this, the way we formulated this problem is not the only way we've done this. We could have defined our x to be anywhere we want. There's an uncountable infinity of places we could put x. There's only 2 that actually make sense: the ground or the top of the building. So we could have come along and define force in the other direction. So I could have defined force from the top of the building, where we start off at 180 and increase by 20 pounds over 12 feet for every foot. In this case, our work, oh, and done that for some small change, delta y. So our work would have been our force times distance. But we would want to note that we are now integrating, instead of integrating x equals 0 to x equals 12, we would be integrating y equals 0 to y equals 12. Our discrete delta y still needs to become a continuous dy. And we're going from 0 to 12 instead of from 0 to 12. And we still get to 2280, which is good. If these did not agree, then one of them is incorrect. Now you might observe that that since our force is changing linearly over this distance, that we could have just found the average weight, the average force, and multiplied that by the distance. To find the average force, in this case, since it was linear, we just add the 2 and divide. However, if this changes in some other fashion, then we wouldn't just add the 2 and divide. It's one of those weird artifacts of teaching people what an average is, where you add everything up and then divide by the number of things. So it starts off at 120, or sorry, it starts off at 200, it ends at 180. Could we use an average of 190? Well, if we take our 2280 and divide it by 12, yeah, because it was linear. We just add the 2 and it was changing linearly. But finding the 2280 was not the point of the problem. Finding the 2280, we do this in both ways to verify that our method works. And we only get to find the average by adding 200 and 180 and dividing by 2 because of this. We would only be able to average the 200 and the 180 because our changing force is linear. If the changing force is not linear, so if I say it decreases from 200 to 180 by some decreasing exponential function, then you can't just find the average by adding the 2 and dividing by 2. You have to do addition in terms of calculus, which is integrating the exponential function from one end to the other and dividing by the length of the interval. So you'd have to integrate anyway. Remember, since integration is multiplication, but one of the factors is continuously variable, that means integration is addition over a continuum. And so in that average calculation, when it says add up all the values, you integrate because we're adding up over a continuum. And instead of dividing by the number of things, since there's an uncountable infinity of things, we divide by the length of the interval. Any questions? Which is the most shocking realization as a teacher, when you realize that you might flunk a student, might pass a student that can integrate anything that you put in front of them, but doesn't understand that integration is multiplication, but one of the factors is continuously variable. And that means that integration is just addition over a continuum. And you might flunk a student that understands, that really grasps that integration is addition over a continuum, just because they can't do trigonometric substitution. This is what I refer to as a crime. Our penalty for this is all the parents in our comment section. Why don't you just teach them the way that I did? Why do you have to do all this place value stuff? And the only reason that parents post that is because someone did try to teach them place value. They didn't learn it. They forgot that someone tried to teach it to them, and now their ego is being bruised because they can't do their fourth graders' math homework, which they're trying to do for their fourth grader. And it's like, listen, mom and dad, you don't need to take the fucking class. Get out the way and let your kid do the work. Stop trying to, quote, help them. Because you're not helping them, you're doing their work for them. You know what I mean? And then this same generation still tries to make fun of young people because they don't know how to change a tire. And it's like, oh, listen, motherfucker, if you don't teach people how to change a tire, they won't know how to do it. If your kid doesn't know how to change a tire, that's because you didn't teach them, dumbass. Anyway. I only taught high school for 3 years. You could probably tell why. And then I'm like at a community college. Like if your parents call me, I don't talk to them. I'm like, oh, I can't tell you how little Johnny's doing in my class. You'll have to ask little Johnny. And then I can't help but editorialize. I'm like, oh, maybe you did something wrong to make little Johnny afraid of you. And that's why he won't talk to you. Maybe you need to work on your parenting skills so that little Johnny won't be so afraid of you anymore. And he'll be able to talk to you openly and freely about his troubles. And they're like, well, I'm going to yell at your dean. And I give them my dean's number. And then my dean called me. It's like, well, why do you got to be such a pain in the ass? I don't know. Anyway, yeah, we could have found the average if all we wanted to do was find out how much work it took to do this for whatever reason. Then yeah, maybe we would have done that. But that would have short-circuited our ability to set this up. And tomorrow, I'm going to give you a different function. I'm going to say, okay, this is what made it easy. Let's make that more difficult. We now have an exponential function going from 200 to 180 over 12 units. So if you want a preview of that, then do that problem. But that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. See you later.